We tend to look at massive concrete buildings and assume the ground beneath them is completely static and permanent. But beneath the surface, the Earth is in constant motion. Soil shifts and erodes, gradually masking flaws that could threaten the heavy loads above. To understand exactly what is happening below ground, the Institute for Infrastructure Engineering and Sustainable Management, or IEESM, was brought in. This schematic illustrates their mission. The Institute was tasked with mapping the unseen foundation of a targeted building to confirm its structural integrity, focusing their investigation along two distinct paths, Line A and Line B. The engineering challenge here is one of access. The team needed a way to inspect the structural elements buried deep underground without having to excavate the site or destroy the existing foundation. To solve this, they deployed ground-penetrating radar. As we can see in this diagram, a GPR device works by sending radar wave pulses directly into the Earth. When those pulses hit a buried, solid object, they bounce back to the surface. Because different materials reflect these signals in unique ways, the returning waves allow engineers to map steel rebars, utility pipes, and hidden voids. To guarantee the credibility of the data, the entire scanning process strictly adhered to ASTM D6432-99 standard procedures for subsurface investigation. By mapping the invisible terrain, GPR allows engineers to pinpoint specific subsurface vulnerabilities and address them long before they manifest as physical failures at the surface. With the data collected, we can now look at the 3D rendered GPR scans, starting our descent right beneath the concrete. This render shows the shallow depth, from 0 to 0.3 meters underground. Isolating the elements in this layer reveals a distinct, orderly grid. The steel reinforcement bars and utility pipes are exactly where they are supposed to be, indicating consistent structural integrity below the surface. However, the radar also picked up a subtle complication at this shallow level, clear signs of moisture and dampness surrounding the concrete elements. Moving past the structural grid, the scan continues into the intermediate depth, between 0.3 and 1 meter down. This section displays a uniform block of data points. These even radar reflections indicate no major, dangerous voids sit in this layer. Yet within that block, faint, irregular shapes pulse through the data, representing scattered, weak radar signals. In a GPR evaluation, these weak signals point to the potential presence of small hidden voids, or water pounding within the Earth. If water pounding goes unmanaged in this intermediate layer, it gradually erodes the surrounding soil, which can eventually cause the ground above to become undulating and uneven. Sinking past the 1 meter mark, the investigation enters the deep layers, pushing down to 5 meters and beyond. The readings here are highly consistent. The deep soil strata appear continuous, showing a stable geological base beneath the structure. There are no significant anomalies detected, meaning the building is safe from massive sinkholes or catastrophic fractures hiding in the deep earth. Looking at this cross-section of the 1 to 5 meter depth, continuous horizontal strata are interrupted by subtle wave anomalies, showing weak signals persist at these extreme depths. This indicates pooling and trickling water actively interacts with the soil deep beneath the building. This presents two competing realities. The building currently rests on a structurally sound geological base, but it is simultaneously exposed to a constant flow of unmanaged moisture. While the deep foundations are holding firm right now, the continuous presence of water trickling down to 5 meters creates a long-term vulnerability that has to be addressed. The IESM investigation ultimately delivered a clear verdict. The building is structurally stable. Across all tested depths, the scans found no major voids or severe cracks, fully satisfying the stringent requirements of the ASTM standards. However, infrastructure stability is a dynamic condition. Maintaining the structural integrity requires active, ongoing maintenance. To ensure that stability, this timeline outlines the first engineering recommendation: implement routine GPR monitoring every 2 to 3 years. Additionally, the team recommends limited destructive testing, such as concrete coring, to physically extract samples and verify the radar data. But the most critical and immediate recommendation is to execute a comprehensive drainage assessment. Managing surface water and ensuring it channels away efficiently from the foundation prevents those weak signals from evolving into active subsurface erosion. The current three-dimensional GPR dataset will be archived, serving as the definitive baseline for all future comparative studies on the site. By utilizing spatial GPR mapping, engineers have proven the building is safe today, and they have provided the exact diagnostic map required to ensure it remains standing for decades to come.